I'm going to do an example of a problem where we change the pressure of a gas phase reaction and think about how the equilibrium will respond. So this is my gas phase reaction. As you can see, all the products and all the reactants are in the gas phase. You can do this with reactions that have just some of the products and some of the reactants in the gas phase. What you're really paying attention to is the gas phase concentrations and pressures and how they're changing. So let's write an equilibrium constant expression. Okay, so that's our equilibrium constant expression written in terms of concentrations. And we can think of concentrations when we think of gases because gases have a certain number of moles of gas molecules in a certain amount of space, and they're always going to take up the space that they're in. So if we increase or decrease the space that they're in, we're going to increase or decrease their concentration. So let's look at what happens when we increase the pressure. So say I have this reaction going on in a chamber and it's at equilibrium, and we have some of kind of each kind of molecule. I'm not going to say which types they are, but you've got a certain amount of CO, you've got a certain amount of H2, a certain amount of CH4, and a certain amount of H2O in here. Okay, now imagine that we cut that volume in half. So now we have the same amount of molecules in a smaller amount of space. And so if you want to think about, well, I guess I've cut it down by a third, not a half. But in any case, we have kept the number of moles. So we have concentration equals moles per liter. And we've kept the number of moles the same while decreasing the volume that they're in. Okay, and so because the denominator is decreasing in value, you're going to get a larger concentration when you increase the pressure there by decreasing the volume. So really these pressure situations, changing pressure, are the same as changing volume. You can think about it in either way, but we're increasing the concentration here. And so let's see what happens. So let's say that here, when it's at equilibrium, I'm just going to plug in some hypothetical values here. And I don't really know what the equilibrium constant is right off the top of my head. It doesn't matter. What matters is how Q compares to C. So I'm going to just plug in some values here. And I'm going to say that it starts out, the concentration starts out at 1 molar for all of these. Not starts out. At equilibrium, they're 1 molar for all of these. And I don't want to try to propagate the misconception that the products and reactants will have the same concentration at equilibrium. They don't always, but in this case, I'm just making it be that case for the sake of this thought experiment, just to make the calculations easier. And so this is going to equal 1. 1 times 1 divided by 1 times 1 times 1 times 1 equals 1. Easy enough. So that's K. Okay, so that's at equilibrium. Now let's think about something that may or may not be at equilibrium now. So we can't assume that it's K. These are all K and Q in terms of concentration. We can't assume that it's K anymore, so we're going to call it Q because we can't assume that it's at equilibrium. So let's go through this thought experiment. Let's say that the concentration of each of these is now it has now doubled. Well, it doesn't look in my drawing like it's doubled, so we'll say it's gone up 1.5. Okay, that'll make my calculations a little bit more complicated, but that's okay. The point is I've changed these concentrations all by the same amount because I've done it by changing the volume that they're all in. And this is before any shift in the actual reaction has happened. So this is just me giving all of these same molecules that were there before less space to move around in. Okay, so in doing so, we've increased the concentration. And so that is now 0.44. Okay, so how has my ratio of products to reactants changed? It has changed to favor, it's changed more in the denominator here because of this exponent. So we're taking that to the power of 3. That makes the denominator change faster than the numerator, and that makes Q a smaller number than it was before, so when it was K. So now we are definitely not at equilibrium because this Q value is not the same as the K value. In fact, it's smaller, so Q is smaller than K. And when I like to compare Q to K, I like to ask myself, well, what are there too many of? And if Q is smaller than K, and if products aren't in the top of both of these expressions, what it means is that there are too many reactants. So the denominator is bigger with respect to the numerator for Q than it has to be for K. So when Q is less than K, there are too many reactants. Too many, and I'm going to put that in quotes because it really doesn't care what we say about it. It's too many reactants for that equilibrium, and so it will shift toward products. Okay, so that's so it's going to shift this way. Too many reactants, so it will shift towards the products. Okay, and so if we increase the volume, thereby decreasing the pressure, now let's say that we've done this. We've made our container, we've increased the volume of it, still have those same number of particles floating around. Then let's see what Q is now. So let's say that it's decreased. The concentration of everything has now decreased because we've given it more space, and so the denominator in the concentration is larger, right? So now let's say it's, I don't know, 0.5 molar times 0.5 molar over all those same concentrations, because we're changing them all the same amount. It's just that one of them happens to be taken to the power of 3 in the denominator there. Okay, so I'm decreasing all the concentrations, but I'm decreasing the denominator faster than the numerator. Okay, so now I get 4. So now Q is larger than K, which means there are too many products. Okay, and therefore it will shift toward reactants this way. So this is increase pressure and decrease the volume, and this is decrease the pressure and increase the volume that way. Okay. Another way to think about this without actually calculating Q's is when you go to the right in this reaction, you're decreasing the number of molecules, and when you go to the left, you're increasing the number of molecules. So when you increase the pressure, then the reaction will shift in the way to decrease the pressure a little bit from there, and the only way that it can do that is to produce less gas molecules, so it shifts to the right. If you decrease the pressure, then it will want to produce more molecules in order to increase the pressure again, so it will shift toward the side that produces the more gas molecules, which will be left.